Okay, we are at section 18.5. That is the macroscopic description of an ideal gas. But before we get into that, I'm going to discuss some of the parameters that we'll be using during our discussion, and we're going to switch to my iPad. And here we go. So these are some of the parameters that we're going to be using as we discuss this. And we're going to start with the lowercase n. N is the number of moles of a substance. Well, what's a mole? A mole, it's not mole, it's mole, is Avogadro's number. N subscript A is 6.022 times 10 to the 23. 10 to the 23 what? Well, 10 to the 22, 10 to the 23 anything. So if you have a mole of marbles, you have 6.022 times 10 to the 23 marbles. Now that's a lot of marbles, and we don't use it to discuss marbles, but we do use it to discuss gases, elements, molecules. So Avogadro's number is 6.022 times 10 to the 23. Lowercase m is the mass of the amount of gas that you have. Capital M is the molar mass. Now, what is the molar mass? Well, if you look at I've got a section of the periodic table here, carbon, nitrogen, oxygen, silicon, phosphorus, and sulfur. We'll concentrate on the top three. The number immediately under the chemical name, carbon is 12.011, nitrogen 14.007, and oxygen 15.999. You can get this periodic table if you go to iupac.org. I forget what it stands for, but that's where I got this periodic table. We'll use the number right under the element name. So the molar mass of a mole of carbon is 12 grams per mole. Nitrogen is 14 grams per mole. Now, you would think that oxygen is 16 grams per mole, and it is if it's oxygen, individual atoms of oxygen, but typically oxygen is O2. O2 would be two oxygens together, so a mole of oxygen molecules is actually 32 grams per mole. Carbon dioxide, you take the 12 plus the 32 that you get with O2, and you end up with 44 grams per mole. Carbon monoxide, you take the 12 and the 16, add them together, you get 28 grams per mole. So that is what the molar mass of these elements and molecules are. Okay, so that'll help with some of the first equations that we see. And then we're going to talk about the ideal gas constant, R. R is equal to 8.314 joules per mole Kelvin, or that's also equal to 0.08206 liter atmospheres per mole Kelvin. Now, wait a minute, liters atmospheres doesn't sound anything like joules. How do we get that? Well, one atmosphere is equal to 101,325 pascals, and a pascal is a Newton per meter squared. So one atmosphere is 101,325 newtons per meter squared. And 1 liter is equal to 0.001 cubic meters. So 1 liter atmosphere is the 0.001 cubic meters times 101,325 newtons per meter squared. So you get 101.325 Newton meters cubed divided by meter squared. Well, you'll see that the meter squared cancels out the cubed, and all you're left with is Newton meters. Well, what are Newton meters? They're joules. 1 liter atmosphere is equal to 101.325 joules. Now, if you take 0.08206 liter atmospheres per mole Kelvin, and you multiply that times 101.325 joules. I should have written joules per mole Kelvin. Sorry about that, mole Kelvin. you'll end up with 8.314 joules per mole Kelvin. Okay, then we also have Boltzmann's constant, KB. There's a lot of K's in physics, so we specify Boltzmann's constant, K, with a little capital B subscript. And if you take the ideal gas constant, R, and divide it by Avogadro's number, you get 1.38 times 10 to the minus 23 joules per Kelvin. And I've got it here, right here. The 8.314 joules per mole Kelvin divided by Avogadro's number, 6.022 times 10 to the 23 moles, you get 1.38 times 10 to the minus 23 joules per Kelvin. All right, now let's get back to, let's stop this share and go back to the PowerPoint. So the ideal gas law, we studied the thermal expansion of solids and liquids. Gases are not, they take the shape just like a liquid does, but even more so, they take the shape of the volume that they're in. And the density is going to depend on the pressure. There's a lot of pressure, then the molecules are colliding one into the other very quickly. If it's not a high density gas, if there's not much pressure, there's the mean free path until they collide is much larger. And really there's no such thing as an ideal gas, but if the pressure is low and under the certain conditions that are discussed in your book, you can very well approach the ideal gas. So here's what we were talking about. N is equal to the mass of the N is the number of moles, and you get that by the mass of the gas that you have divided by the molar mass. That gives you N. And that N is what we use in the ideal gas law. PV equals nRT. Pressure times volume is equal to N times the ideal gas constant R times the temperature. So you'll see this relationship. If pressure goes up, then the temperatures will go up. If the if the volume decreases, the temperature has to decrease. You'll see the relationship there in the ideal gas law. PV equals nRT. And the R here, as we discussed, is 8.314 joules per mole Kelvin. It's also 0.08206 liter atmospheres per mole Kelvin. This is the champagne bottle. Let me switch. Again, I've got a little drawing to help. People think that you shake a bottle of champagne and you've increased the pressure, and so the cork pops. But what really happens is, let's change color so you can see what's currently in this section here. You've got the gas, and if you shake it, that gas gets mixed in with the liquid underneath, under the pressure, the initial pressure, which is much higher than atmospheric pressure that it was when it was bottled. And so if you release the cork, these bubbles in here expand. Each one of them expands, and that's what shoots out the champagne. Now, let's see if I can get rid of all these little blue marks. If you tap the sides and the bottoms and to where there's no more bubbles, you'll return the gas to this chamber up here, and when you release the cork, you won't get the outflow that you normally get. But the point of this slide is to dispel the myth that shaking the bottle of champagne increases the pressure. That's a myth, and now you know why that's not true. Okay, now we're going to talk about Boltzmann's constant. PV equals nRT. That's our ideal gas law. P is pressure, V is volume, N is the number of moles of the gas, R is the gas constant, and T is the temperature in Kelvin. Now, if we take N, the capital N, here is the number of molecules divided by the Avogadro's number, you'll get PV equals NKBT. You'll get the Boltzmann's constant, where the Boltzmann's constant is equal to the ideal, gas constant divided by Avogadro's number. And I showed you that in the handwritten notes, that is 1.38 times 10 to the minus 23 joules per Kelvin. Okay, let's, a common material for cushioning objects in packages is made by trapping bubbles of air between sheets of plastic. Is this material more effective at keeping the contents of the package from moving around inside the package on a hot day, a cold day, or either hot or cold days? In other words, it doesn't matter. What do you think? Well, on a hot day, the molecules, the temperature is going to increase, so the pressure is going to increase. Remember, PV equals nRT. So if T increases on one side, the pressure has to increase on the other side, because the volumes that, well, I mean, I said that wrong. The pressure is going to be, should be the same, but it's going to increase the volume. So on a hot day, it's going to, it'll be more effective. Okay, how about on a winter day, you turn on your furnace and the temperature of the air inside your home increases. Assume your home has a normal amount of leakage between inside air and outside air. Is the number of moles of air in your room at the higher temperature larger than before, smaller than before, or the same as before? Well, as you heat your house, if there's leakage, it's expanding, and some of the molecules are escaping out, so there's fewer moles in the air. It's smaller than before. Okay, and that ends the discussion here. I will do some example problems. I won't tag it on to this video, so it won't be that long. I'll do a separate video where I'm doing sample problems. So we'll stop this recording, and I'll do the problems on another video.